I think probably today we will not yet go into these references that I told you on quantum thermalization, or maybe we will. I brought my computer, but I'm not sure if I'm going to start there. But I was told that many of you thought this Gaussian part was too fast. So I think this was my mistake. So I was told that in the tutorial, most people had skipped problem 1 in the first day. And I interpreted that as saying, oh, I'm tired of this. I know this weak theorem and I know all this. But I think you probably jumped it because you thought these are just a bunch of integrals. I don't care about integrals. I want physics. So maybe I should do it more calmly, this Feynman integration part and the graphical interpretation a bit slower again. I think it will do no harm. Okay? So I'll do some, I'll recap the Feynman integration and the graphical rules that we could assign if we want. No one obliges us, of course. We are just computing integrals, so we can just compute integrals. But we can have some nice graphical interpretation as well. And I'll discuss a little bit these Gaussian integrations in a second. But before, let me summarize a little bit some of the things that we have seen before. So we had a table, right? And at each point of our lattice, we had a height x at position n that could the table could go up or down. And then we consider the propagator, which was the expectation value of the height variation at position n and height variation at some point further away. And we saw that this propagator, xn and xn plus m, was given by this expression here, where this quantity here was this effective frequency of oscillator k. So it's a Fourier transform. We sum over all modes in the Brillouin zone that are from -pi to pi with spacings of 1 over L, roughly. And that's the expression, and that's exact in the model we solved. Then if the table is large, I can replace the sum by an integral. And if we are at large separations, which means that m is very large, I can further expand out k at small momenta, and I end up with a propagator like so. Notice that in the intermediate step of the computation, we wrote each of these guys as a Fourier mode. So in the intermediate step, we compute this expectation value in Fourier, which would be also a propagator, but we don't propagate from one position to another position. We propagate from one Fourier mode to another Fourier mode. And what do we see in this propagation? In this propagation, we see that the mode k propagates directly, and it's like you inject momentum k, and k plus k prime must be 0. You have momentum conservation because we have translation invariance. So systems with translation invariance, they have momentum conservation. And that's just what we see here. And then, so these modes propagate trivially. There's no non-trivial propagation between a mode with momentum k and one with k over 2. K just propagates directly to minus k. What comes in goes out. And this is just a propagator, is what dresses the Fourier transform here. And the statement that at large separations I can expand the signs is the statement that I could ask, what is this propagation at small momenta? And here I will just replace, it would be the expression where I replace sine square of k over 2. I just expand out and I replace it by k squared over 4. Right? So it's the same business, it's just basically this. Okay? And then, so then we said that if we had various lattices, they would change the prefactor that would dress here. So it would mean that it would change this effective mass here. But that's all we would care at large distances from our propagator. The various possible interactions would give me an effective mass, which, when we go to large distances and see that the propagator decays exponentially, we recognize that this parameter here is rather physical. We can think of it as an inverse correlation length. It tells me on which distance is the correlator starting to decay. So it decays after this distance m, 1 over m effective. So m effective is like an inverse correlation length or a mass scale. So by the way, let me just make one comment that you have seen in the lecture, in the tutorial, sorry, that in d dimensions, if we are not in a table, but if we are in d dimensions, what would change? Nothing, basically. All that would change is that d2k would go to ddk, right? Or rather, d2k over 2 pi square would go to ddk over 2 pi to the d, right? And we could also ask about the large distance separation in d dimensions. So let me tell you that we did it in one way in the lecture. So let me actually do it in another way. I don't know if that's how you did it in the tutorial. But let's suppose we wanted to study here large separations. And one thing we can do for large separations is notice that at large separation, this integral oscillates a lot. So because this integral oscillates a lot, what happens is, if I think of my contour k, if I go deform it up to the imaginary plane such that this is exponentially suppressed, what I want to do is to deform it up as soon as possible, as much as I can, because as I go up and I take it complex, this would become exponentially suppressed rather than oscillating. So that's the general idea whenever I have this kind of integrals, is therefore the first singularity I encounter, the first obstruction to moving it up, is what will give me the large distance behavior, right? Because if there was no obstruction, I would just move the contour and it would be exponentially small and it would just be 0. It's the fact that I have some obstruction to moving it up. The first obstruction is what will dominate the large distance behavior. So what's the first obstruction? Is the pole here when k is equal to im, right? So the relevant region will be the region of k close to im that will dominate the integral, right? And one way of seeing it, for example, is by doing a saddle point computation. I can think of this integral as e to the minus I k dot m minus log of k square plus this effective mass square. And what will happen is that close to the saddle point, as I said, we are going to be close to the pole, so the logarithm is going to explode. M is very large, so the exponent is going to explode. So all this is very big, and there is a competition between the two terms. And we can look at the saddle point. And let's see what the saddle point gives me. The derivative with respect to k gives me minus I m mu, the component mu of the distance, minus the derivative here just gives me k mu with a 2 divided by k square plus m effective square, right? And this should be equal to 0. And now, I'm not going to continue the algebra, but let's just say by words what we would do. Now, for example, I would bring this to this side, square both sides. That will give me k square, right? Because then it becomes k square over function of k square equal to m square. So I will compute k square by putting this on this side and squaring it. And now that I have k square, I know that k is that function of k square that I computed times m mu. And I'm done. And then I plug this k into the exponent and I expand that large separation. Okay? And that's it. So when we do it, on the saddle point, we see that we get e to the minus mass effective times the separation. Okay? Which was the same result that we had before. Okay? So is this trivial? Just put this on the side, square, get k square. After you have k square, put the k square here, put this on this side, and you get k equals something times m. Now you are done, and then just plug it here, and you see this result at large separation. Okay? So one thing you can see, you will see solving this equation, is that what we said is true. K squared to leading order is minus m effective square. Right? This term is very large. This term wants to be very large, so k squared wants to be close to minus m effective square. As it should, of course. Okay, good. So that's an example. Good. Now, one thing we also said was that this thing here, right, this computation, or this one, they were both just Gaussian integrations, right? And now, if you remember from Gaussian integrations, we had the following statement. that if you have a Gaussian integral, the integral of dx1 up to dxn, right? And then I want to consider some quantity, let's say dot, 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 e to the minus x dot a dot x. Let's put over 2 because it's convenient. And this a, I can think of it as a symmetric matrix. And if it was not symmetric before, it is symmetric now because I'm sandwiching between xx. So whatever is the antisymmetric part is projected out, right? If a as an antisymmetric part, it just dies. So I can take a to be symmetric. And I want to define average of this dot, dot, dot to be equal to this Gaussian integration divided by the same thing without the dot, dot, dot. And we said that one way of doing this is by saying that this is the same. If I call this bottom integral here z, we can say that this is 1 over z times derivative with respect to some auxiliary current j, I1, derivative with respect to some auxiliary current j, This is now I'm specifying to dot, dot, dot being equal to x I1 up to x ik. Then what I could do is I take a bunch of derivatives of a partition function that now depends on a source, and I set the source equal to 0, where this partition function now with the source is just the same integral where I add some extra source here. And now the basic idea was that I could compute explicitly this object, and this object, the explicit computation, gives me a number. That number is not very important, but we can fix it in a second. But what's important is it gives me exponential of 1/2 j dot a minus 1 dot j. It gives me this times, and then I complete the square. So what remains is z with j equal to 0. Right? Because you remember, I just completed the square. After I complete the square, I call the new variable x minus whatever, I call it y. So that integration over y just is the same as the original partition function, so it's the same. And what remains when completing the square is this thing here. And therefore, we see something nice. We see that, so this here I can call z. I mean, of course, this was just z, but in particular, it's z with j equals 0. So the z with j equals 0 cancels when taking derivatives. And I see that this is equal to, so this, by this, I mean, I'm continuing the computation. So this is a remark. This is a definition, and then I'm continuing. Right? So this is equal to the z0 cancels, and I get derivative with respect to j I1, derivative with respect to j ik. And now I'm going to do something smart. Okay? I'm going to do the following. I'm going to act with these derivatives on this exponential and then set the j to 0, right? So this exponential contains many terms. I can expand this exponential. I can write 1 plus exponent square plus exponent cube. And most terms give 0. Why? Because most terms, for example, if they have few powers of j, they get killed by the derivatives. And if they get too many powers of j, the derivatives kill some powers, but not all, and then when I put j equals 0, I get 0. Right? So of all these terms, right, if k is an even number, like say twice m, the only term that survives from the exponential, so we get a bunch of terms, plus the only relevant one, which is 1 over m factorial times j dot inverse dot j times 1/2 this to the power m, this to the power m, plus dot dot dot. So these are higher powers. So these guys have too many j powers, too many j's. So after taking derivatives and setting j to 0, I get 0. And these guys, they have too few powers. Right? And therefore, when I take k derivatives, I get 0. And therefore, all I have to do is take derivative of this term. Right? And now, you see what happens is that we have 2m terms that need to act on this polynomial of degree 2m in j. Right? And this, after I take all the derivatives, right? After I take all the derivatives, what happens? I get a bunch, after I take all the derivatives, I will get a bunch of a minus 1s, a minus 1, a minus 1. There are m of them. We took the derivatives, now there are no more j's. And what about the indices? Well, the indices depends where the derivatives act. They can act, it can be everywhere. So it could be, for example, it could be, let's see, how do I write this? Right? So the derivatives, I1, I2, they could be, say, on the it could be here, if the derivatives act here and here, or they could be in different positions if they don't. So let me write like this. Let me say, what's the best notation to indicate this? Sorry. So there will be a summation, right? The derivative act, and I sum over all possible pairs, right? All possible ways of making pairs, and then I have so this sets me all possible pairs. So I make all these indices into pairs, a prime, b prime, etc. Right? So I take all these indices I1 up to ik, where k was twice m, and I make all possible pairs with these indices, and then I just get all possible pairs here. And the claim is that this is the full result, and this is what's called Wick's theorem. And this summation over pairs is what we call summing over weak contractions. That this is just names. So before understanding the meaning of these names, let me just point out that the fact that this is an equal sign in particular means that I'm claiming that this m factorial and this 2 to the m just vanish. And that's just because the derivatives, when I have two derivatives, they connect first here, then here, or first here, then here. That explains why the 2 cancels. And because when the derivatives finished acting, when I say that 1 and 2, they act on the same A, they can act on this first pair, or the second, or the third, or the fourth, and that will cancel the m factorial. Okay? So all in all, this is the final result that we get. We just sum over all possible pairs of this inverse of this matrix A. So the particular case is when I just have a propagator between I1 and I2. This is just the inverse of my matrix A at I1 and I2. Right? Which means that my matrix A, Ij times the propagator x, j, k, right? This is the definition of inverse. It is just delta ik. Right? I just multiplied by the A by A, and I see that my propagator is the inverse. So the propagator is the inverse of the matrix that appears in the Gaussian integral, right? So the propagator is the inverse of A that appeared in the Gaussian integral. Now, notice that this was exactly what we had before. For example, when we had this Gaussian integration, in Fourier modes, it was just a single integral between k and k prime. In other words, if I want to write it as a matrix, that Gaussian integration matrix is a matrix which is diagonal, and it only couples modes k and k prime. So the inverse also couples modes k and k prime. And because it's a diagonal matrix, the inverse of that matrix, it is just take whatever was there and invert it, flip it. So this 1 over this is just inverting the matrix. It is nothing but the inverse of the matrix, right? So if you remember, that's why this is the frequency omega k. And this is just the inverse of the quadratic matrix that was multiplying xk and xk prime. Right? And similarly, if I think that x's, they were coupled, then I would say that my original action, my original Lagrangian, from which I computed this, was nothing but a bunch of x's, a vector x which represents all x and m, dot some a dot some x, where this matrix here, it's almost diagonal, but it was also off diagonal a little bit. It coupled neighboring modes, right? So it will not be exactly diagonal matrix, but it will be almost. And then what is this expectation? Well, according to that, it is just the inverse of this matrix, right? Evaluated at positions n and n plus m. What we did was we computed that inverse by going to Fourier, and this is what we got. So going to Fourier was diagonalizing that matrix. And today, you are seeing in Dan's lecture a propagator of a scalar in a free scalar quantum field theory, which is very much the analog of the continuum limit of what we were doing in the table. So what are the key differences between what Dan is doing and what we are doing, and how do we see some similarities? For example, here is one similarity that we can see. The last equation Dan wrote was saying that notice that the propagator is a Green's function. So what does it mean? It means that this object here, acting on the propagator, gives the identity. This equation is nothing but this equation that I wrote here. That I have whatever multiplies, sorry, here it was xx. Whatever multiplies the quadratic form, acting on my propagator, gives the delta function. So in the continuum limit, this, for a free field that Dan was doing, right? It's exactly what we have. The free field, the action, is some integral over d dx d phi square plus m square phi square, right? Which if you integrate by parts becomes the integral d dx phi minus box plus m square phi. So you can think that this object is just the analog of A, and what we have here is saying that this object times my propagator is equal to 1. So this propagator is the inverse of this object. In the same way that for us the propagator was just the inverse. The second thing is that in Dan's case, you would have a derivative. You would have a spatial derivative. Versus what we had, which was a discrete derivative. Right? So this is just a discrete derivative. So when does a discrete derivative become a continuum derivative? When things change slowly for long wavelengths. So of course, our object, if it changes slowly, so for large wavelengths, we can say that this object is just some derivative. It just becomes some discretized derivative. It just becomes an approximation. If the function changes slowly over my lattice, if I'm considering long wavelengths, it is just the same as a derivative. And therefore, in our action, right, our action, this interaction term, xn minus xn plus L, is very much becomes, in the continuum limit, as an integration over the position dn of some derivative square. So it's not a surprise where I'm calling x phi just to make the connection even more clear. So it's not an accident that at large distances or large momenta, our propagator became basically Dan's propagator. Right? K squared plus m squared in both cases. Because it had to. We are looking at long distance. The final difference is that Dan has some annoying signs. He has an I, he has an I epsilon, and he had some funny contour. Right? And we have none of that. And we have none of that because we are doing Euclidean physics. Dan is doing quantum mechanics, and we are doing thermal physics. So Dan has time, right? And we go from quantum mechanics to statistical mechanics by weak rotating time to I tau, right? This you have seen in my test course, right? Am I right? So how do you rotate? How do you rotate? You take time and you rotate to I time. And in doing so, you take P0, which is the energy, and you rotate to I energy. So Dan was saying that this is the contour, but this is perfect because the poles are here, Dan was saying. But then I can perfectly rotate it into this contour where this would be I times the energy, I times P0. And when doing so, what I would call P square here would become minus P square, right? Because now all components become negative. P square minus the P spatial part becomes just minus a total vector, which now is all the components, right? And also, D4P contains the D energy. The energy becomes I times this D new D, that I cancels this I. So all in all, after this weak rotation, this dense propagator would become precisely what we would get from our table at large distances with a proper identification. Okay? So we are very much discussing the same thing from a different point of view. And even this notion of weak contractions, if I understand correctly, will come about in Dan's lecture tomorrow, I think, right? This idea of summing over weak contraction. You did earlier today. So even this has a parallel story there. Okay, so I would like to, I would like now to go on and discuss couple of things here on these Gaussian integrations. But let me first point out that if these computations are clear, that's all there is. We are just doing computations. We are computing some physics, but we are doing some Gaussian integrations. I wrote as a sum of weak contractions, so it's very tempting when you are summing over pairs to start drawing lines that connect pairs, right? It's almost unstoppable. We can almost not control ourselves, and we will do it, but we don't need to. So there's nothing. When I start drawing fancy pictures and saying fancy words about these weak contractions and what kind of diagrams we get, which we call Feynman diagrams, they are just associating a picture to each term in this expansion. And now it's up to us. I mean, I like one type of pictures. You might write another type of pictures. Each one can draw whatever pictures we want, right? So don't try to attach too much to one particular person's choice of pictures, provided it also works for you. Yes?
But it isn't trivial that when you take the continuum limit, you would get to the quantum field theory case, right? To a continuum field. Or maybe in this case, but in general, it's not trivial, right? You could have weird phase transitions or things like that.
No, I'm just saying that, of course, we are studying a classical system with thermal fluctuations, right? And we could study a quantum system with quantum fluctuations. And both problems, they are not independent, because there is a connection between problems in quantum mechanics in d dimensions and problems in statistical mechanics in one more dimension, in d plus one dimension. And that you get by weak rotating between the two. Okay? Now another problem would be to consider a quantum problem with finite temperature, but that's more complicated indeed. Okay. So let me go on and okay. Right. So what we are seeing is that if I have expectation value of x I1 up to x, say I6, for example, what I can do is I sum over all possible pairs. So let me write a few. I1, I2, A minus 1, I3, I4, A minus 1, I5, I6, plus other pairs. So how many terms there are? Let's see how many terms there are in total. So x1 needs to choose someone to be paired with. So x1 has 5 choices. Right? So x1 chooses someone. So say x1 chooses x6, for example, or x2. Then we go to the next x that is free. The next x that is free will have 3 options, because there are now three other free. So we get 5 times 3 terms in this sum. Right? 5 options for the first x I contract, I pair, and 3 for the remaining one, and then only 2 are left, so there's only one option. So it's 5 times 3 times 1. Okay? And in general, so the general case, if I have expectation value of x1 up to xn, or up to x to n, because only the even ones give non-zero result, it would be 2n minus 1 for the first guy, 2n minus 3 for the second guy, and so on, which is what we call this double factorial. Right? So because of this, for example, let me actually continue here. If I have expectation value of x to the 2n in a usual Gaussian integral, right? This is just a usual Gaussian. I can say that this is expectation value of x, 2n times, and then I form all possible pairs, and there are this number of pairs, so this is just this times 2n minus 1 double factorial. That's how many terms there are. And each propagator, if it's normalized in a canonical way, would give me 1 over alpha, and there are n such propagators, right? N such expectation values of x squared, right? So this 1 over alpha here is the expectation value of x squared, which is the value of one pair, right? So this is the result. One Gaussian integration gives me this, and where I have this. So what I can do is say that this is, it's my choice, of course. I can say that this is 1 over alpha to the n times 1 plus dot 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 plus 1 this many times, right? Times 2n minus 1 factorial factorial. I'm going to raise the blackboard. Right? So that's just my choice, I just said. And this, I can think that this has an interpretation. It's like I have a vertex with 1, 2, 3, up to 2n. Okay. And then all I'm doing is contracting this in all possible ways. So I can connect this leg with this leg. I can then connect this leg with this leg. And then I connect the remaining two, say this one, with this one. Right? And if I count how many ways there are, of course, by definition, 2n minus 1 double factorial. And therefore, I can say that I sum over all such diagrams. Right? This is just interpretation of this result. The result is a sum of all such diagrams with the statement that a line, which is the propagator, is just a factor of 1 over alpha. And then I sum over all possible ways of connecting the lines, and whenever I see a line, I give a factor of 1 over alpha. And this would be a very simple example of what we would call a Feynman rule. Now, of course, it would be overkill. We are just computing a Gaussian integration, which was something simple. And we are saying it's a sum over all possible graphs. And each graph has a propagators, has a bunch of propagators. Okay, it's fine. But it's correct. Okay? So what about in this example? In this example, the same. We say that this object, I could think of it as an object which is a vertex with I1, I2, I3, I4, I5, I6. And then I sum over all possible pairs, which means I connect them, say, like this, and like this, right? And I sum over all possible diagrams with now a more sophisticated line, because now the line has two endpoints. It connects I and J. And when it connects I and J, it gives the inverse of the matrix evaluated at I and J. So now it's a little bit more interesting because I have various indices. And therefore, this matrix could be 0 for some choices, not 0 for some other choices, and so on. Okay? But again, this is the equation, and this is my choice of drawing it like this. Okay? It is just because I find it convenient. Okay? So this would be a more complicated propagator, and this would be another way of representing this expectation value. Okay, now with this in mind, with this explanation, let's consider then a more realistic theory, so we see how this could come in handy when we are considering a quantum field theory. So let's go back to our table. And let's ask, what is the correction to my propagator, to my correlation function between displacements at positions n and n plus m, in the presence of a nonlinearity mu, which we take to be a small nonlinearity. So any question about the Gaussian integration? Does it clarify some of the things we said yesterday? Is it clearer now? Or are you equally confused? Was this helpful? Was it a waste of time? Okay. Back to our table then. So we want to compute a displacement in the presence of a small nonlinearity. So what are we doing? We are saying that we have our integral, right, over all our positions, the xn product, right, e to the minus beta sum over positions xn square plus we add some kappa over 2, I think, sum over neighbors xn minus xn plus L square. So this was the Gaussian integration part. Right? And then we would have the mu in the exponent that I bring down, and I say that this is 1 minus mu beta sum over n xn to the 4 plus mu square beta square over 2 factorial sum over n and m xn to the 4 xm to the 4 plus dot dot dot. Right? And all I'm doing is expanding the exponent, and all this is multiplied. Okay, this was a bad idea because I used here n and m, and I'm using there n and m. So let's change here because this didn't appear yet. Let's put here position I, and displacement, say, x. Okay? And now we have this times xi plus x. Right? And this is all divided by the same thing without the xi plus k plus x. Okay. Well, but this, now that I expanded down, what we have is expectation value of a bunch of x's in a Gaussian integration. Right? So what do we have? Let's see. What we have is that this is therefore equal to the expectation value xi plus x. Yeah, it's a bit funny to use x downstairs and upstairs, but okay. This is small x, big x. Okay, xi plus x. And now these averages stand for averages in the Gaussian, which is the same as to say free theory without mu. Right? That's the first term when I put mu to 0 everywhere. I get this term. And then I would get minus mu beta sum over n expectation of xi plus x xn to the 4. That would be, say, from the leading term in the from the first term in the exponent. Let's suppose we want to do linear term in mu first. And downstairs I would get I would also expand out, so I would get minus the expectation value of xi plus x times, so it's downstairs, so I expand, I get plus mu beta sum over n expectation value of xn to the 4 plus order mu squared. So to linear order in a small perturbation, this is how this would change. Okay. Now, let's see what this term would be. Okay, let's call this term. Let's now study this term. Okay. So this term will be equal to the sum of pairs. Right? So we'll sum all pairs of expectation value of two x's, right? Of this guy with this guy with one of these guys. So there are 6 x's here in total. So it will be exactly like the case that I wrote there. I1 up to I6, there are 15 terms, right? So there are all these possible terms. Now, when I sum over pairs, now it's quite convenient to think of it like this, that I have x, okay. Yeah. Before doing this with contractions, let's do one more step before. Let's say that this term there is minus mu beta, and then I have a bunch of x, and I want to do it in momentum space, not in position space. So we'll have to write lots of sums, but let's do it. So we get sum over n. That one was already there. Then for xi and xi plus k, each of them I write as a sum over k and then sum over k prime. And each of them comes with 1 over L. So in total, there would be L to the 6 because we have minus. So each of them we're going to Fourier. And then for the x to the 4 with Fourier with respect to k1 up to k4. And then each of them gives me an exponential. So we have e to the I k, oh, beautiful idea. Okay, ki. So this I and this I, one of them is square root of minus 1. E to the I k prime I plus x. Okay, so one I is a vector, it's a position, right? Okay. And then the other one, e to the I sum over this k, j, up to 4 dot n, right? And that's the one where we sum over n. And then we get expectation value of xk, xk prime, xk1, xk2, xk3, xk4. Okay, so it's this expectation value here that I want to think as a sum over all these pairs. Right? So each term will be a sum of 3 pairs. There will be 3 pairs of propagators, and I sum over all possible ways of making pairs of these guys. But before, let's simplify this a little bit, noticing the usual thing, but very important, this step. Sum over n, this sum over n, is conjugate to this total momentum at that vertex, and it ensures that this is 0 unless this total momentum is 0. So this sum over n sets k1 plus ... plus k4 equal to 0. Right? Do you agree? Now, in each pair here, in each pair, we have 0 total momentum. Right? In each pair, we have k and minus k. Whatever is the momentum of the first guy, the second one needs to be minus k. We said these were diagonal. So in total, we have 0 momenta, because we have 0 momenta for each pair. Right? And because k1 up to k4 already add up to 0, we know that this k prime must be equal to minus k, or otherwise one of the weak contractions will be 0. Right? So k prime or one of these weak contractions will be equal to 0. Right? Because the k's already add up to 0, so total momentum must be 0. And therefore, we know that k prime is actually equal to minus k.
Right. What are these brackets now? Like the very top line. What's good?
Sorry, it's pairs. So this is expectation value of 2 x's. Right?
Any two. Okay.
Right. So we sum over pairs. So let me maybe make that step a little bit. I think here there is one step that we could make. Let's add here one more comment, which was that we had this general weak theorem, right? But then we also saw that for a single pair is just the inverse, right? So another way of writing weak theorem is not in terms of A, but say that this is nothing but the expectation value of xa prime. And this is nothing but the expectation value of x as well. So another way of saying is that in a Gaussian integration, the expectation value of xi1 up to xik is a summation over all possible pairs I can make of then the product of x a1 a2 ... x a k minus 1 x ak, where a1 up to ak are just all possible pairs I can make out of I1 and ik. And now in this formulation, there is no matrix. It is just if the integral is Gaussian, and if you know the 2-point function, you know the n-point function. Right? So this is in a Gaussian model. If the model is Gaussian, we know the 2-point function, we know the n-point function. So that's what we are using here. We are knowing this is a Gaussian model. So I know the 2-point function. So this 6-point function is equal to a sum of product of 3 2-point functions. And for each 2-point function, momenta must be k and minus k. So the total momenta adds up to 0. But this momenta adds up to 0. So these two must add up to 0. And therefore, all these sums simplify a lot. This sum over n sets this and gives a factor of L squared. Right? This gives L squared times delta function. So in total, we will get minus mu beta over L to the 4 sum over k e to the minus I k dot separation x. The annoying I disappeared, so it's good. It was just there for one intermediate step. And now only the separation appears, which is good. And then we sum over all momenta that k1 plus dot 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 plus k4 equals to 0. They add up to 0. Expectation value of xk, x minus k, xk1 dot 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 xk4. Yes?
The sum over n doesn't necessarily have to fix the, like it could fix the sum of the from k1 to k4 up to a constant, right? Not exactly 0.
Can you be more specific?
Yeah, like in there, we assume that as the, well, as I understand, we assume that as xn does not depend on k and we're doing a Fourier transformation. And the sum over n over all the modes should require that the sum over k over the momentums is 0.
Yeah, I'm just using this mathematical identity. Summation over all positions n e to the I n k is equal to L square delta k equals 0. Where k now is this sum of vectors. Okay, so now we have to compute this summation, this computation here. We have to do this computation. So what do we do?
Question? So in that expression, the xi and xi plus x are not in the same relation function as
There?
Yeah, so how did we group all 6 x's?
No, this is just, you see, this term.
Oh, sorry.
Okay, so let's continue. So this expression, right, is equal to minus mu beta. I'm actually going to write it like this: minus mu beta 1 over L squared times sum over k, because that's the natural object that transforms into integral d2k over 2 pi square, right? This goes from minus k to k in steps of 1 over L, so there are L terms there. So this is the one that has a nice limit. E to the minus I k dot x, and then I put the other 1 over L square here. Sum, where the total momenta k1 plus k4 equal to 0, of this expectation value that now I write as all possible pairs. So I'm going to write it like this. I'm going to write 2 pictures, and then I will explain. This is one picture, and this is another picture. Okay. So what do I mean by this picture? So this picture means the following. So here I'm thinking that I inject momentum k, and I receive momentum k here. And this line here represents the propagator, the pair xk, x minus k. That's one term where in my pairs I pair the first 2, xk and x minus k. And what about the other ones? Then I pair, say, k1, for example, with k2, and k3 with k4. So this would be the expectation of x, k1, x k2 with x k3 x k4, right? But it could be also 1 with 3. It's a by this expression here. Let me write. This comes from such pairs. From pairs like this, not exactly only this one, but also 1, 3, 1, 4. From all pairs that only involve this interaction term. But what are they in the end? So each propagator here sets k1 to be minus k2. This one sets k3 to be minus k4, right? So automatically they add up to 0. Great. So this constraint is irrelevant, right? Automatically they add up to 0. So this computation here, this graph here, is just the sum over the momentum k in the top bubble, right, of this two-point function in position space that I will call propagator with momentum k top, where this propagator is just this expectation value. I'm defining the expectation value, the propagator with momentum k. I define this expression here to be this g0 of k. Right? So it is just the two-point function in momentum space. Right? So it is just this is equal to g0 of k. That expression there that we wrote. And then, what is this computation? I put momentum k1, let me call it k top. So I say that here there is some top momentum flowing, and it goes in and goes out, so it's conserved. And here there is some bottom momentum, so I sum over k at the bottom, g0 of k at the bottom. Right? But you see that, and how many ways are there of getting to this term? Well, k1 could connect with k2, k3, or k4. So k1 would have 3 options. So there would be a factor of 3 for this graph. Because there are 3 pairs that end up giving the same picture, end up giving the same expression, right? What I call k top could be k1, k2, k3, but it's just a summation variable anyway. So there are 3 graphs that would give this picture, which is, you see, a product of 2 terms. I could also write this as saying that this is just a propagator, where I have some momentum k getting in and getting out, the same momentum k, and I sum over it, so I do a loop like this. That indicates a sum over k. And there are 2 terms that are the same. So I could just say it's the square of this term. Because it's just one propagator here that I sum over k, one here that I sum over k, and they just give the square of a single loop. Okay? Yeah.
Are the sums over k top and k bottom not already in the sum over the sum that you have outside the brackets? Or are they different? They're different sums.
Sorry, so this sum tells me sum over all momentum that add up to 0. But then from these pairs, automatically I see that this must be equal to minus this, and this must be equal to minus this. So automatically they add up to 0. So I can replace this sum by these 2 sums. Right? So these 2 sums are what was before that original sum. So in other words, when I put this arrow, I should say that this first term is this g0 times this sum, and then I remove this sum here. Right? So this term, this picture with this sum included is what this is. Right? What about this term here? Here means that I take k, I inject momentum k, I receive momentum k here. But now, you see, I put one propagator between k and this vertex, and then momentum k goes here, and then momentum k goes there. So this would come from terms, from pairs like And this would come from pairs like xk, and then it could be, for example, k1, and then say k2 could couple to k3, and then k4 would couple with x minus k. Right? So k enters the vertex, then 2 goes to 3, and then 4 goes to minus k. So this would be if the labels here were 1, 2, 3, 4 for these 4 x's here. Right? This would be this pair here. But how many pairs there are like this? Well, k could connect to k1 or k2 or k3 or k4. So there are 4 options for who k connects to. And then there are 3 guys left that could connect to minus k. So in this case, here, there are plus 4 times 3 graphs. Like this. Where this graph now represents, in equations, this graph is one propagator here, so 1 G0 of k, one propagator here, so another G0 of k, and one propagator here that we sum over. So summation over the momentum on this bubble, let's call it a bubble. Just names because we are summing over, doesn't matter. Propagator of this k of this bubble. And that would be the expression that we would associate to this graph.
Shouldn't there be a contraction between 3 and 4?
So this graph means k connects to one of the terms in the vertex, and then one of the terms in the vertex contracts to minus k. Now, which one? I have many options. That's why I have 4 times 3 here. One of them is the one you said, where instead of 2, 3, I have here 3, 4. And then here I have 2, 3, 4. So 1 and 3, 4, 1 and 2 are left. So 1, 2 would be here.
Okay, then how can you close the 3 and 4 there in the diagram?
You see I made a typo here. So 1, 2 and 3 are here, and 4 and minus k are here. Yes? What was your proposal?
Because you have a contract.
So here I'm contracting k with 1, 2 with 3, and 4 with minus k.
Okay, I understand that.
Right? So you add on one other proposal, which is connect 3 and 4,
Yeah.
and then 1 and 2 are left. So it will be just replace this 4 and this 2 here in this picture. And that is another of the terms. So there are 12 options here. Again, this 12 is there are 4 options to connect k, and then after I connect, minus k has 3 options left. So that's why there is 4 times 3. And let's make a check. A check is that in total we have 3 terms plus 4 times 3, and that's equal to 15. Right? And 15 was the number of terms that we wrote in the blackboard that is hidden. Right? So 15 is how many terms we said there are. Right? So it's good that we now see that it's convenient to separate these 15 terms into these 2, because they have really a different expression. And we did the counting correctly. They add up to 15, as they should. And now, notice furthermore that this term here is disconnected, and this term here is connected. Right? It's a connected graph, and this one is a disconnected graph. And notice that nicely, the disconnected term cancels with this other term that your colleague asked about. So this other term, let's go down here. Now we can think a bit about this. Well, this term here, there's nothing to do. There is just a single propagator, a single line. There's a single pair, right? And here I have a vertex. And what I do is I contract in all possible ways, but they are all equivalent. So there are 3 ways, because this guy, I choose which one to contract with, and then I'm done. Right? So indeed, this graph gave this times 3 times this graph, just by all possible pairs. And therefore, it immediately, this graph immediately cancels this one. So this disconnected one cancels. So you start seeing the usefulness of these graphs, right? If I were to now go there and go to Fourier, rewrite sum over pairs and so on, it starts to become painful. But now with some experience with graphs, we draw a bunch of cartoons right away and we say that cartoon cancels this cartoon and we are done. Right? So it does make computations much faster. And therefore, all in all, we conclude that our propagator is equal to, well, this guy here was 1 over L squared sum over k e to the minus I k dot x. That was the first one, times a propagator in Fourier, G0 of k. And that guy we represented as just free propagation. We just said this is a graph where they just propagate. It is just a 2-point function. That was the first term. And now let me factor out, let me write it already here in Fourier space. So in Fourier space, we had this term, which was, as I said, just a propagator, plus this term, which was 12. There was a minus sign, so minus 12 mu beta, minus 12 mu beta. Right? No, not 12. Yeah, 12, that's correct. 12 mu beta. And then we got, this was this term, G0, G0, and G bubble. So we get 12 times G0 of k squared times what is just a number, which is a sum over momentum, let's say Q. I chose Q. Q is just G0 of Q. And this picture was, I have my propagator, and I have 2 propagators here, and I have 1 integrate summation over the momentum Q that goes there. And that's what this term here was giving me. Right? And then we would have plus order mu squared. Right? So the conclusion here, or there are a few things now I want to say about this result. But the conclusion is that we have a bunch of effective rules, or effective Feynman rules, it seems. And the rules is that because we have this weak theorem underlying, this implies that in practice, all we have to do when we want to consider this propagator is we imagine we have some incoming position k, some outgoing momentum minus k, right? And if I'm doing it in perturbation theory, right? So at order, say, mu to the n, I would have a bunch of mu vertices. So this would be one vertex, another vertex, another vertex. So this would be, say, n equals 3. So for n equals 3, I represent this to indicate x k1 up to x k4, and this would represent x k5 dot 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 x k8, and so on, right? And then what would happen? Summation over this corresponding position would set momentum conservation here. At each vertex, there is momentum conservation, right? That comes right away from the summation of the corresponding position. That's just translation invariance, right? And then what are we instructed to do? Consider all weak contractions, which means draw all possible graphs where you connect the various things, say like this, for example. And what you are instructed to do is sum over all possible graphs where you connect this with what is the rule? The rule is that each vertex will give me a factor of mu times beta, or maybe minus mu times beta in our conventions. Each line would give me a factor g0 of the corresponding momentum. For example, here momentum is conserved, so what gets in must get out here. So this is q, it must be q there. Right? So each propagator connects some momentum q. Right? So here it could be q prime, and then this line would be g0 of q prime. Right? And then we withdraw of all other graphs and sum over the momenta in loops. So whenever there are momenta that are unfixed, like here, for example, or like here, I say momentum is conserved. K goes in and K goes here. Well, I still don't know what I have here. I could have Q here and minus Q. So I have to sum over Q because I don't know what it is. Right? If I have a more complicated graph where I have, say, these two loops, I would have to sum over Q and over Q prime. This is compatible with momentum conservation. Right? And finally, let's put here, and count. To be careful to put these correct factors of 12 and so on. Yeah? And this is what Feynman graphs, this would be what Feynman graphs are. And what's important to emphasize is that this is very general. What was important? Was the form of G0 of K important? No. All right, do another lattice and you have a different omega square of K, fine, it's okay. Right? Doesn't matter. The only thing that matters is that you have a Gaussian theory, which is free, plus some perturbation, which is some polynomial. The polynomial is of degree 4, then your vertices are squares, are crosses. If your vertex is of degree 6, your vertices will have 6 lines getting out. If it's of degree 3, it's 3 lines, it's an intersection, right? It's a Y symbol. So you will have this kind of construction with summation over graphs and weak contractions. What was crucial here is, one, to have a free theory to start with, a free theory that is a Gaussian theory, and then to have polynomial perturbations. Right? So for us, we had x to the 4, so we had a square. If it was x cubed, it would be a y shape, etc. Then immediately, the free theory tells you what is the propagator, and the perturbation tells you what are the vertices of your graphs. And then you know the propagators, you know the vertices, you draw all the graphs you want, and that's how we would compute systematically in perturbation theory.
You always cancel the disconnected graphs?
That's an excellent question, and the answer is it actually depends. So if you consider, for example, 4-point function, you could have a product of disconnected contributions, where you have like product of two 2-point functions. So, and there, no, you would indeed have a disconnected, a genuine disconnected contribution. But vacuum graphs, yes, you do always cancel, because there are always weak contractions, which are just the boring ones amongst the things you put, and the rest is just vacuum stuff. It is just stuff about Z. But those will also be downstairs, so they will also cancel. Now, Z itself, the denominator, what we write here, this expression here, which is Z, is a sum of what are called vacuum diagrams. Because it has no external x. It doesn't have an xk and an x minus k. So we just draw bubble diagrams, right? So this guy was, for us, this bubble plus, and then it would be, say, bubble square at order mu square. But you could also have a term like this, right? So this would be two terms that you could draw as a graph using a quartic interaction and so on. And this would be vacuum diagrams for Z. And what is true related to this connected is that you see that even for Z, the graphs are not connected. There is a bubble, but then there is, say, this 8-figure square, right? As I go to order mu square, I can have x to the 4 times x to the 4, and each of them, right? The square is like expectation value of x to the 4 times expectation value of x to the 4. Is itself disconnected. It's one of the terms that appears in Z. So for Z, you have to draw all graphs, connected or disconnected, assign the rules that we set to them, which is that, for example, here, we would sum over momentum Q1, Q2, Q3, and Q4 that add up to 0. They come from the same vertex, but we would have still a sum over various momenta there. Right? So we would sum over all these momenta here, and we would sum connected and disconnected graphs. And it's actually a nice exercise, but one that I would not strongly recommend you to do, simply because I think you will do it in detail in quantum field theory too. It's a simple exercise to show that log Z is a much nicer object, because log Z is just the sum of connected graphs. So what is Z? Is the exponential of the connected graphs. Right? So you just exponentiate. So this term, even though it's here, it is just 1/2 of this guy squared. Right? And the other disconnected ones, okay, they are here, but secretly they are just exponential of something much simpler. Okay? So Z is the exponential of connected graphs. Then if you expand them down, the exponent, you get products of them, and those are all the disconnected. Okay, so I want to make two more comments. I want to make a few more comments in the remaining 5-10 minutes. So one comment is that we saw that this is one term, and then we had this other term, and then at order mu square we have many terms we could draw. Right? We have many possible fluctuation effect. Now, I would like to resum a particular class of diagrams to illustrate the kind of thing that a full a full nonlinear computation with all powers of mu could give. So what I want to do is, okay, so summing, one idea would be, let's sum over all graphs. But that's too hard. No one can do it. That's one of the challenges in quantum field theory, is that perturbation theory, even though it's cute, we have some diagrams like I showed you. In practice, you can do 1 or 2 bubbles, but more bubbles is too hard. You get too many integrals to do. It's just too complicated to list all the diagrams and so on. So it's hard to draw all the diagrams. So all graphs is too hard. So let's do it. Let's sum a subset of graphs. That will give us already some intuition of the kind of things that can happen. And this subset that I want to sum is the following. I want to say that I have the free propagator. Then we have this term. Now, this was exact so far. So far, there's no approximation. But then at order mu square, I just want to sum iterated bubbles. So I want 2 bubbles plus 3 bubbles plus 4 bubbles. Now, these are not all the graphs, because this graph, right, it comes with a minus beta mu square from these 2 guys, from these 2 vertices. But there are other graphs of order mu square, like, for example, this one, right, where I inject momentum k, I get momentum k, and that momentum gets split into k1, k2, k3, where these k's add up to k, right? Where the sum of these 3 momenta is k. Momentum is conserved. So this graph is also of the same order, and it's way harder than this, because this is just a number, and this is the number square. Right? So this graph is not harder than this one. It's just the square of the previous one. This is really a new quantum effect. It's really a new effect where the particle splits into 3 and joins. This one is a complicated one. So let's do just this one here. So let's see what we get. So this thing here, more rigorously, was minus 12 beta mu. And then we have this propagator square, that's this horizontal line, times this bubble. I'm just breaking it apart. Now, this term here, let's write more carefully. There is minus beta mu square, right? But now let's write all the numbers. Let's do the counting. So this guy came from expanding the exponential twice, right? We brought it down from the exponential twice. Do you agree? We brought the interaction twice. So already there is a 1 over 2 factorial from expanding the exponential, right? Then we said k connects to one of the vertices, right? One of the 2 vertices that we brought down. Which one? It doesn't matter. And there are 2 options. So there is a factor of 2. So this is for which vertex k connects to. This is from expanding the exponential. Okay, so we had 2 options, and we said k connects to the first object. But to which line here in the vertex? I have 4 options to choose. Right? And then of the 3 ones, one of them connects to the next propagator. So I have to choose which one. Now, here I have to choose which one connected to that guy, 4, and then which one connects to minus k, 3. Okay? Do you agree? Just ways of counting. So what happens is that 2 cancels with 2. This 4 times 3 is 12. So in total, we got minus 12 beta mu square. So it was just a square of the coupling of the first graph. Okay?
Can you please explain it again? This 4 times 3.
Okay. 4, we can say, now that we said that k connects to the same vertex, this is which leg in that vertex k connects to. I mean, this is one way of counting. Of course, each person can have its own way of counting, right? I mean, I'm just thinking of ways of counting pairs in one way. Now I said k connects to this vertex line. Now, that vertex still has 3 more lines. So I choose then of the remaining 3s, right? Of the remaining 3 legs, I choose a volunteer, right, who connects to the next vertex. Now that's the 3. Now that leg goes there. And then, where does it attach? Right? Where does it attach on the other vertex? That's a 4. And finally, who connects to minus k of the remaining 3? Right? So the constant is just the square of the previous constant. And then how many propagators we have? 1, 2, 3 propagators with k, and 2 bubbles, which are just the same square. Sorry. Three propagators and 2 bubbles, right? 1 propagator, 2 propagators, 3 propagators, and 2 bubbles. And then it's easy to see that each term, it's just going to be this power, and then I increase these powers by 1. So all in all, I'm getting propagator. I factor it out. 1, that's from this term. Let me call this term alpha. 1 plus alpha propagator bubble plus alpha square propagator bubble square plus dot dot dot. Let's write one more term. Plus alpha cube propagator bubble cube plus dot dot dot. But that's just equal to propagator divided by 1 minus alpha propagator bubble. Propagator is 1 over a denominator, right? So we conclude that this is equal to 1 over, so the propagator is 1 over a denominator, which is this denominator here. Well, let's write it explicitly. 1 over beta m omega k square, which is omega square plus 8 kappa sine square of kx over 2 plus sine square of ky over 2. Notice that this is the first time we are, up to now it was totally general for any Gaussian theory, and now we are specifying to our theory. Minus alpha, but minus alpha was plus 12 beta mu times this bubble, where this bubble is just a number, right? This is just a number, and that number is just 1 over L square sum over Q, the propagator, which is 1 over this same propagator with Q, right? Instead of K. Okay? And this would be just a number. Right? So what happened in the end? What happened in the end is that after all this computation, what is the functional dependence that I get? I get a very similar functional dependence where I have an extra constant here, right? This is just a constant. Like this is a constant. Right? So in practice, what I can think is that this is redefining my omega. So the net effect here is that I can think, at least in this, for this subset of examples, that I'm just shifting my omega square to some, say, physical omega square that would be equal to omega square plus 12 mu over m times this bubble. Right? In other words, it's what this is doing is just redefining this effective mass, which was basically, this effective mass was basically omega square up to some kappas. So if you divide by some kappas, this is just redefining some this effective mass. Right? So what would it mean? It would mean that at large distances, if I now go and redo the analysis of what's the propagator at large distances, the computation is the same. Except that where I see this M effective, I put M effective prime, where M effective prime is the shifted M effective by the new constant. Right? Because from the point of view of the computation of now what this would give at large distances, you see that the K dependence is all the same. Right? The K dependence is the same. It is just shifting by a constant, this omega here. So at large distance, it still decays exponentially, but M effective changes. Right? Or more precisely, what I'm learning is that my M effective, which is a macroscopic quantity, also gets corrections from these nonlinear terms. And these nonlinear terms are renormalizing my, my bare parameters and changing them into the physical ones. But here, everything is finite. This number is finite. It is just a summation of L terms of a bunch of finite terms. So everything is finite because we have a lattice. So there are no regularizations, no divergences, as in usual renormalization here, because things are finite. Right? But what we have here is a mass renormalization, a finite mass renormalization, in the sense that the net effect of this resummation of effects would be just to change omega to some physical omega. So if I measure it, that's the omega that I would measure by studying the decay. You agree? Now, notice something. Notice now something cute that I'm just going to mention it, and then we'll come back in future lectures, which is that this is because we have a lattice here, right? Here we have a lattice. So we have a lattice, so all our expressions are perfectly finite and there is no problem at all. But suppose we have a table and we don't know the lattice details. I'm not sure if it's nearest neighbors or next to nearest neighbors or if diagonals also couple. I only do experiments at long wavelengths, right? So I don't have access to the really microscopic details of which neighbors connect with which neighbors. In other words, I could first think that I zoom out, and then I go to this language here. Right? So this is what we see when the details of the lattice are washed out. Right? This is what we'll get, the propagator, where I expand the sine square, the wavelengths are long, and I expand the sine square, and I don't see the details of the lattice. But if I were to do it in this bubble diagram, if I take the bubble where I use the long wavelength approximation, this would be the integral over d2q over 2 pi square, 1 over q square plus m effective square, right? I'm just replacing the sum by an integral. And now I have a problem that this is divergent. Because if you see at very large q, this goes like q dq in radial coordinates. So this diverges logarithmically. So this is logarithm of some cutoff if I say that I integrate up to some large momentum. Right? What is this large momentum? This large momentum is like the inverse of some small distance. So it's like saying that because I lost the details of the lattice, now it looks like I have some divergence. Right? So what would I conclude if I were to do the computation already with the lattice washed out? I would have this term here, and it would give me a divergence. It would give me infinity. Right? So it means that I go to this term, and when I am in this already long wavelength limit, I get here a divergence proportional to log of my cutoff. Right? But the physical mass that I measure is physical. It just decays with some exponential limit. So the way we say it is that these parameters here, that were the bare parameters, I could absorb my ignorance about the lattice by saying that this guy was the physical one minus this log lambda divergence. That would be something big that I don't know of. And that what this divergence would be doing is I know that the net effect is for them to cancel and give me something that I measure. And that's something important, that there is sometimes ignorance about large k, which we don't have. We know the propagator exactly, and we know that there is no large k. K goes between minus pi, and all this is totally finite, the sums we do, and everything is regular. But if I were to consider replacing a sum by an integral, and then I think that k can go to arbitrarily large energies, which means arbitrarily small distances, it's as if I don't have a lattice to regulate. Now I have infinitely many modes, and I start getting divergences because of this ultraviolet catastrophe. But we know that there is a lattice there. So we just put some cutoff to regulate these sums and say that the lattice will fix it. And that's what adding this usual, then we would go into the domain. In this case, this would be usual renormalization. But we are going to discuss this in more detail. It's just to give you a little flavor of a toy model where for us, the table, everything is finite. There are no divergences, there are no infinities. All renormalizations will be finite renormalizations because everything is finite. But we can easily understand that if we were to first take the continuum limit and wash out the details, some expressions such that these bubbles would start becoming divergent, and we would take care of them not by a finite mass renormalization, but by a divergent mass renormalization such that the physical results are finite. And that's what you will also see in detail in quantum field theory 2 and later in this course. Okay, so on Thursday, we'll study a quantum table. I want to show you a quantum table, which is just a bunch of modes that hop around, of bosons that hop around in a lattice. And it's going to be a small lattice because quantum is harder to simulate. So instead of doing, how long did we do? 60 by 60, which is a very big lattice. 60 by 60 is how many? It's 3,600 sites. We will do 21 sites. And we will try to thermalize a table with 21 sites, but quantum mechanically. So I think it's a good exercise because the math is totally different from the usual one. Yes?
How do you know what the effect of ignoring those other diagrams is?
That's a very good question. So all I know is that by summing these graphs, I'm putting in some more corrections. All this is always assuming that beta mu is small such that these are perturbations. I'm just assuming that I'm including a little bit more of the result. But you are totally right that these graphs are super important. I would need to compute them. And they would renormalize further the mass. They could change the behavior. They are important. That's the only thing. So the full propagator with all the correct dependence on the position, it does receive contribution from this graph as well.
You still get correction to omega that's linear in mu.
Actually, why was it linear in? Yeah, from this graph here. No, for sure no, because this graph only shows up for the first time at order mu square. Right? So there are two vertices, so there is mu times mu. So this is what we'll call a higher order effect. Right? So to linear order in mu, what we did is correct. It was just keeping these two terms. Right? And you can interpret what I'm written here as just a smart way of writing 1 plus x is 1 over 1 minus x. Right? And then it's downstairs, because downstairs we know the computation already. Okay.
So we can say that this is an exact correction for order mu.
This is, so
Up to order mu, this is exact correction.
yeah, up to order mu, this is exact. Yeah, up to order mu, this is exact. Yeah. Yeah, the propagator is perfectly equal to this to order mu. So what we are doing here is exact to first order. But it's an approximation at higher orders.